Thank you very much for the introduction. Yes, so I picked this because I've noted a certain skepticism among many quarters of academia and even industry as well, as to whether AI is going to turn out to be another thing that, people think will revolutionize fuzzing, but then it turns out that throwing more cores and more executions per second ends up doing better. So this is a deliberately inflammatory meme on the right-hand side there. Somewhat dangerous to give to a room of software engineering experts, but nonetheless, I think that it is certainly the case that over the past 10, 20 years, we have seen many systems that attempted to sort of be more effective by adding some kind of much more sophisticated analysis, and that often making small tweaks to something like a plain coverage guided gray box fuzzer would end up surpassing that. Okay. And part of the core problem is something that Thomas alluded to very well in his keynote this morning, which is that it's much easier to scale up processor speed and core count than it is to make things much, much smarter, right? Okay, well, but maybe this is different, right? So we do actually have something genuinely new, I think, which is a couple of years ago. In fact, feels like longer ago than it really is, but back in March of 2023, we actually got some fairly sophisticated language models, okay? And they are actually changing a number of things quite quickly. So apparently there are 1.3 million people paying to have one of these models help them code. I would be one of them, but they actually gave it to me for free. So I'm not one of them, but I do use it. And it seems like there are many areas where you can take fields that have had lots and lots of really good work and good research over the years and throw these somewhat general purpose language models at them and end up doing close to state of the art. Okay? And this despite the fact that at base, they don't necessarily know things about programs. They are dealing purely with text. Okay? But at the same time, there are also plenty of places that you can find where they have not really lived up to hyper promises. And one of these might be if you ask a language model, is this function in my source code vulnerable, right? Is that going to reliably tell you whether there is a vulnerability there? It turns out no. They're very inconsistent at saying that. They're very prone to false positives and things like that. So I think that what I'm going to try to do in this keynote is make some sort of argument that there is a place for using AI and language models to help fuzzing, but that it won't necessarily look like the things that maybe first spring to mind when you think about applying them. Okay. So I'm going to go through sort of three case studies. One is one that I think is sort of a very unpromising use, which is trying to use a language model directly to generate inputs for your fuzzing campaign. The second, which I think has gone quite well, and there are, I think, plenty of folks from Google who can attest to this, that generating fuzz harnesses for something like libfuzzer, that often works quite well. And then I'm going to talk about some kind of more speculative things. These are mostly things that I just think are neat and that I think could be useful, such as using them to essentially generate little programs that create good seeds for the program under test. Okay, so let's start off with the bad news. So, I think I've talked to lots and lots of people who heard about language models, said, oh, this is great. They're very good at modeling input distributions. And then you sample from them, and you get to basically sample from this nice model distribution, but in a kind of stochastic way that you can control and maybe will introduce some random errors, right? And so that almost actually sounds kind of like what you would want from a fuzzer, because you get something that matches some input distribution pretty well, but that then can go off the rails in a kind of controlled way. Okay, so there's a lot of work from even quite a while ago, back before the advent of modern language models like the transformer. So Patrice Godfrey had this actually very nice paper, and I don't mean to pick on him here, where they took a recurrent neural network and used it to learn basically what PDF files look like, and then use that to generate mutated PDF files for fuzzing. Okay, and so I claim that this doesn't actually work very well in practice. Why? So there's two reasons. One is that if you compare a language model to essentially any other kind of fuzzer, it is an astonishingly slow way to generate inputs. Okay? The second is that they are very data hungry, right? So you need many, many samples typically to get a decent model of this input space, which raises the question of where you're going to get those samples. So first of all, what is the very fastest you can sample from a language model right now? So there is a company called Grok that builds dedicated hardware accelerators. And these are essentially hardware designed to sample from large language models as quickly as possible. They can go at a blazing fast 1,250 tokens per second for a fairly small model, an 8 billion parameter model. And unfortunately, if you multiply that out, so a language model token typically works out to be somewhere between 3.5 to 4 characters. And so if you multiply that out, that's only about 5 kilobytes per second that you're going to get for input generation. Okay. So now if you imagine trying to stick that in the middle of your fuzzing loop, then your throughput is very, very low, right? You're bottlenecked on how quickly you can just generate inputs at all. Okay. The second problem is the sample efficiency, right? So if we want to get a good model of this file format, then we want maybe thousands of different examples of this input type. And so now I feel like we have a bit of a dilemma, right? Where are you going to get inputs like this? Maybe you can find lots and lots of excellent examples of these inputs on the web, right? There are probably millions of PDFs on the internet. But once you've gone to the trouble of assembling those, it's not necessarily clear why you would use a beautiful corpus like that to learn to train a language model, as opposed to doing something like traditional corpus minimization and using it as seeds for traditional fuzzer. Meanwhile, you could try to do something like run a fuzzer for a while, generate inputs that get good coverage, and then train a model and try to sample from that. But this then is limited by whatever coverage you could achieve in the first place, right? It's very hard to escape that initial distribution. Okay, so that's the one that I think doesn't work very well. So let's talk about one that maybe works a little bit better. And it still isn't perfect, but suppose that you are doing API-based fuzzing, right? So you are using libfuzzer, and this has lots and lots of wonderful advantages, right? You can reach deeper into libraries. You can test specific parts of the code. You can make them potentially much faster because you don't have to do the full program startup, everything like that. But traditionally, this has been quite painful to get developers to adopt at large scale, because there's kind of two things that you need expertise in. One is that it's not actually all that intuitive to write fuzz harnesses from scratch yourself. There are a few kind of non-intuitive things about it if you're just an application developer. And then meanwhile, if you have some fuzzing expertise and you set out to write a bunch of fuzz targets, then you run into the problem that now you have to understand many different programs' APIs, what their contracts are, and how you're supposed to put them together. Okay. And so even before this whole AI craze, there was some good work on automatically generating fuzz drivers. And you can do this without language models. But I'm going to try to make a claim that you can, in some cases, do this slightly better with language models. So just kind of recap, and this is not talking about my own work. I'm talking about excellent work done by folks on the OSS Fuzz team. So in OSS Fuzz, they have lots and lots of these projects that do currently have some fuzz targets, but maybe don't have as much coverage as they want. There are lots of areas in the program that can't be reached from the harnesses they have. Okay? And so back about a year ago now, they did this kind of very cool project where they started generating fuzz harnesses. And essentially what they did was they said, I'm going to take the coverage reports from OSS Fuzz and say, where am I currently not reaching, right? And then show that to a language model and say, now please write me a fuzz harness that will get me to this part of library code. Okay? And you do a couple of rounds of this because maybe the first time you try it, the language model generates something that doesn't compile. But after a couple more rounds, you end up with some very nice fuzz harnesses. And they do actually have some nice results here, right? So they've found, I think, as of about 6 days ago, 14 new vulnerabilities from harnesses that were generated by a language model. And this is quite nice because these are in projects that have been fuzzed for years and years, right? And so they're actually finding genuinely new code to explore without having to spend too much time and effort writing fuzz harnesses by hand, okay? So why do I say this is not as good as it potentially could be? So unfortunately, unlike fuzzing from, say, the main of a program, not every combination of fuzzed inputs are equally valid, right? So if I hand any combination of bytes to a program and it crashes, then that program definitely has a bug. But if I come up with a collection of API calls into a library and it crashes, then maybe they have a bug, or maybe I didn't write my fuzz target correctly, right? So the example over here is one, and this is an example that was made up. So I just made this up by looking at the CJSON documentation, not by generating it with a language model. But you could have a fuzz target that generates a sequence of API calls that talks to CJSON, and it does a sequence of operations that looks pretty valid. So it starts off by creating a JSON object. Then it adds a Boolean value named A. Then it adds another one named B, and it reuses the same reference, okay? And then finally, it deletes the object, right? So when you run this under something like address sanitizer, you get a nice, beautiful use after free report, because in the process of destroying it, it deleted A, and then it deleted B, but A and B refer to the same thing. And so you got a double free, okay? Now, if you went and reported this to the CJSON authors, you would probably get that report closed as invalid, and they would point you to this section in the README, which says that if you want to add a second reference to something, then you need to use something like add item reference, right? That if you add it twice, then you're going to get a double free. Okay, so this is the kind of thing that is very hard to capture in an automatically generated fuzz target, right? The only place where this particular constraint is specified is in that README, right? There's nothing else to say that when you're making calls to this API, you need to use add item reference as opposed to add item. Okay. So now, does this happen in practice? Yes. So this is a follow-up, again, from Oliver Chang, one of the developers who's been doing a lot of work on using language models to generate these fuzz targets. And the problem is that when you're automatically generating these, if you're not careful, then you end up violating implicit contracts that the library needs enforce. Okay? But this, I think, is one area where you could potentially take advantage of one of the strengths of language models. Okay? So first of all, they're language models, right? They actually can take constraints that are specified in natural language and potentially use them to condition what they generate. Okay? So potentially, if you were able to find relevant documentation and use this in conjunction with generating a fuzz target, then you can potentially end up avoiding generating ones that violate even these kind of implicit contracts, or at least drive down the rate at which you end up with these sorts of false positives. Okay. Another area where you might end up wanting to use this kind of ability to actually read English is something like this case. So did anyone actually follow this AI cyber challenge that happened a few weeks ago? So one of the kind of more interesting things to me was that one of the teams, Team Atlanta, actually managed to find a zero-day vulnerability in SQLite. Okay, so most of the challenges, in fact, all the challenges in the AI cyber challenge use planted vulnerabilities. So if a team found them, then it wasn't really a vulnerability they would report to the developers. But in this case, they actually found a real vulnerability that the organizers had not planted there. And it turned out to be this sort of weird feature of this FTS5 module, where if you passed it the right combination of words to this tokenize argument here, then you would end up with a null pointer dereference. Okay. So I actually asked how they would have found this. And it turns out that if you just go and read through the manual and start generating test cases based on what you see in the documentation with some slight modifications, then this pretty quickly can uncover the bug. Okay. But again, this is the kind of thing that you actually do have to go and read documentation for. And maybe you don't want to read documentation for it, but if you can condition a model on documentation and use it to generate initial seeds for some kind of fuzzing process, then you can end up finding these things much faster. And this is quite nice because this means that there's now a large body of work that you can draw on that was written for humans, but that is directly relevant to generating valid inputs or not quite valid inputs for programs. Okay. So the third main one that I'm going to talk about is this notion of now trying to kind of more directly use language models to make fuzzing better. Okay, so these last few have been more about sort of taking things that we could do by hand, maybe by reading lots of documentation, and then trying to automate some portions of that with a language model. Here I'm going to actually try and maybe more directly attack this core problem of how do we generate lots of good inputs for testing a program. Okay? So the main thing that we ran into with that first case study is that language models are very, very slow at generating raw inputs. Okay? On the other hand, they are quite good at writing programs that can then generate inputs, right? So when I say they're quite good at writing code, this is just a result from a few days ago that apparently the most recent OpenAI model is somewhere in the 89th percentile of competitive programming at this point. So it can, in some cases, write very good code. And the nice thing about this is that if you use a language model to write an input generator, that input generator is just regular code. Okay, it can generate inputs very, very fast, even if you're using a relatively slow language like Python. And then what we can try to do is take an initial input generator created by a language model and now actually subject that to mutation and evolution. Okay, so whereas before we were taking as the target of evolution to be the input to the program, right? Now we're going to try and mutate and evolve programs that generate inputs for our target. Okay. So again, here, there's actually some nice prior art from Marcel and colleagues, where they were taking advantage of this fact that language models have a fairly vast background knowledge, right? They're trained on the whole internet. And so you can now get them to do things like write you a grammar for a network protocol. Okay. And this is somewhat similar in spirit because now that grammar can be used to drive a much faster fuzzing process. Okay. So unfortunately here, this is limited by sort of how much the language model already knows about the protocol, right? So it works really well for protocols that are well documented, that have been described many times on the internet, but maybe less well for ones that are custom, undocumented, and so on. Okay, so this is a little prototype system and a very complicated little diagram. But the basic idea here is that we're going to try and start with a tiny little program that doesn't really do much. So maybe it just writes out a valid looking header, and that's it. And then we ask our language model to create variants of it, right? And we can do this in a few different ways. So we still have mutation operators, but we can now use language models to implement various different kinds of mutation operators. So one is you can just say, here's my program. Please rewrite it for me to make it better somehow. You can also take advantage of sort of more specialized capabilities. So some language models have this capability called fill in the middle, where you can essentially delete the middle portion of some text, and it will try to find a something to put in between that joins the two. Okay. You can also use that fill in the middle capability to splice two existing generators together. And then, of course, you can also do things like just throw away all the code after a certain line and regenerate from there. Okay. And so this gives you a set of mutations. And then you can do the classic thing, right? You need some way to decide fitness. And here you have a very natural fitness measure, because you can use your input generator, generate a bunch of inputs, and ask, what sort of coverage on average does this input generator achieve in the target? Right? And so this lets you rank possible input generators. Okay. And so the output of this process is hopefully a family of generators that gives you high coverage inputs from the target. Okay, but as before, okay, so I can show this is the initial one, and this is after about 10 generations. You start to see much more complexity. Here, though, one caveat is that like the network protocol case, the GIF file format is fairly well known. So this isn't sort of the pure result of evolution. This is also drawing on existing background knowledge. Okay. On the other hand, we can actually do better here because we can, if we have access to the program code, we can take advantage of the fact that we can, in many cases, translate between languages, right? So we can take a C program, we can show the language model a portion of the parser code and its existing input generator and say, can you extend this input generator to support this piece of the parser, right? And this won't work very reliably, but it, over many iterations, can end up adding features to the input generator that reach new parts of the parser. Okay. All right. So all this is a fairly complex and elaborate system. And so as an example of how this can potentially work, so on the right-hand side here, I had an initial GIF generator, and I ran it through standard code coverage report, and it said, okay, there were some lines in here that were not getting covered. And so basically just asked language model, here's some code that's not getting covered. Can you update this generator that I already have to support this feature as well? Okay, and it does. And you end up going from something like 90% line coverage to 93% line coverage. Okay, so this all sounds very good. Unfortunately, there is a different sort of bitter lesson, which is that fancy system designs like this can, in some cases, be completely beaten by a better model coming out a couple months later. Okay, so when I first put together that kind of little prototype system, the best models that were available were actually pretty weak. Okay, so I would run it for maybe 10 generations and ended up with a nice little GIF generator that got me 30% line coverage. And I felt pretty good about this because this was up from maybe 5 or 10% line coverage. On the other hand, then after a new model came out, these had much larger context windows. So I could fit a lot more code into the prompt and just potentially even give it the entire code of the parser and then ask it to write me a generator from that. And when I did so, right off the bat in one step, I got a generator that had 92% line coverage. And this was significantly better than the evolved one. Okay, so the bitter lesson there was that in many cases, trying to, and this is the classic bitter lesson from machine learning, in many cases, lots and lots of effort put into trying to come up with clever designs that work around limitations of existing models. That effort might be better spent, I don't know, doing something else and waiting for a model to get better. Okay, so that was a bit sad. Okay, so what might be some other interesting uses? So one way to think about this is that you now potentially have something that, as long as you don't need it to be absolutely correct all the time, can turn implicit constraints specified in natural language or specified vaguely in the intent in some programmer's head, and maybe turn them into code that you can then run and check automatically. So 2 examples here. One might be, can I take an existing program, and fuzzing is really, really good on an unmodified program at finding things that we have good oracles for, right? So if we have something like a memory safety oracle, then we can go ahead and run our fuzzer, and it will give us back crashes, and we know we have bugs. But if we want to test for higher level invariants, right, things that are don't apply to every program, then typically we have to go through and add assertions. Okay? So could we use language models to add assertions? Maybe. That might look something like this. So here, this is, again, a made-up piece of code, but it is for doing some kind of 2D graphics rendering. And it has optimized cases for rectangles and triangles. And I want to add assertions. Now, there is an implicit invariant here that does hold, right? Which is that rectangles are supposed to have 4 vertices and triangles are supposed to have 3 vertices, right? But the only place that's specified, right, is in the name of these constants, okay? And if, again, you ask to turn those into an assertion, that actually can work pretty reliably, right? So we end up with these assertions that a rectangle has 4 vertices, a triangle has 3 vertices, and that an n-gon has greater than or equal to 3. Okay? So that is the case where it works pretty well. But there is kind of an open research problem, which is if you end up with assertions that are not true, then violating them doesn't really mean much, right? So are there ways that we could avoid introducing lots and lots of false positives when generating assertions like this? So one might be to say, let's use the assertions to guide the fuzzer to what we want to try and to an invariant we want to try and violate. And then that input hopefully is getting the program into a weird enough state that even after we remove the assertion, something else will go wrong that violates a more traditional oracle that we can check. Okay. Or maybe we just say, okay, I will just deal with it and look through a bunch of false positives and try to decide which ones are real. Okay. So the other case where this might be helpful are things like cases that currently need lots of human annotation. Okay, so there was a fun paper a few years ago where called PyJon, where they showed that if you were willing to sit down and add some annotations to a program to express things and expose them to the fuzzer. So for example, if you had a protocol parser and you wanted to express to the fuzzer that it was in different states at different times, then you could add an annotation that adds a little explicit state variable and then expose that state to the fuzzer. Or you could take some internal quantity and say that this is something that in my fuzzer I want to maximize, right? And so this is very nice. And they had some fun demonstrations that, for example, if you add a annotation to Super Mario Brothers for the player's position, then the fuzzer can end up learning how to get you all the way to the end of the level. But again, you run into this problem that adding these annotations by hand can be quite painful, right? So this again might actually be a kind of nice case to use a language model for, because the cost of getting it wrong is fairly low, right? In the worst case, you slow down the fuzzer by exposing irrelevant information, right? And trying to maximize the wrong quantity or things like that. But in the best case, you end up capturing something about the state that actually lets you find new and interesting coverage in the program and find real bugs. Okay. So there are some challenges still here, which is that is not a massively popular annotation language. But on the other hand, it turns out that you can just explain how it works. So this morning, I sat down and copied and pasted a bunch of documentation and a few examples of how to do annotations for a particular program, and then asked it to add annotations for a program that I had, and ended up with some things that actually look pretty reasonable. So here we're going to expose things like the combination of frame sizes. So we'll try to explore a bunch of different frame sizes. In practice, I think that'll actually turn out to be way too many new states that it adds, but that's okay because that just maybe makes the fuzzing performance slightly slower. And so now you can potentially start getting some of the benefits of these manual annotation approaches for free. Okay. Now, I was hoping to actually be able to, by this talk, try this out and see if we actually got any improved coverage. Unfortunately, I ran into a problem that is still beyond the limits of current AI, which is getting a research system from a couple of years ago to work on a modern machine. So I was stymied at that point. But this is the kind of thing that, again, I think is a very nice example because it kind of captures a few different things. One is that you're trying to take advantage of the ability of a language model to take implicit constraints, encode them in code. And you're avoiding one of the weaknesses, which is that they're not particularly reliable at doing so. So you want to find a case where when it messes up, it's not going to cause correctness issues. Instead, maybe it just ends up creating irrelevant coverage. Okay, so I guess I will kind of wrap up with just saying roughly what I think of as the main considerations, right? So the really cool things about them are that they have actually seen basically all the text on the internet. So if the thing you're trying to do is vaguely captured by a couple web pages out there, then they may have some knowledge of it already. They're pretty good at writing mostly correct code in popular programming languages. And they can actually be conditioned on things like natural language in a way that's very difficult to achieve with symbolic tools. However, they're also really slow. They're not deterministic. So if you sample from them 10 times, you will probably get 10 different answers. And you get absolutely no guarantees of correctness, right? They are purely text-to-text machines. So where does it make sense to use them? Well, if the cost of making a mistake is very, very low, if you have some kind of automated external verifier for anything that it produces, right? So this is where things like doing vulnerability detection using language model kind of falls down, because if you ask it and it says there's a vulnerability here, now you as a developer spend the next day trying to figure out if it's real, right? And that's very, very costly. But if you're trying to do something where you need really, really low latency and high throughput inputs, then it doesn't really, usually is not going to make sense. And of course, hopefully this one is pretty obvious, but if there's already a good non-language model solution for something, then don't just try to redo it with a language model, because usually you're going to end up with something that is not nearly as good. And I think this morning, as I was talking with Thomas after his keynote, the kind of amazing thing about them is that they make use cases that formerly were completely impossible into use cases that are merely unreliable. And in some cases, that's really amazing. So with that, I am going to stop talking, get some water, and then let people throw tomatoes at me for the next 45 minutes.